All right. I believe we're live here. Welcome to today's session. Where are we at with AutoML? My name is Jeff Toffley. I am Clarify's senior technical writer, and I'll be your moderator today. Before we get started, just a few housekeeping items. All attendees will be muted, but we do encourage you to ask questions, which you can do by typing into the Q&A widget in the top right-hand corner. There's also a chat thread where people ask questions. And we'll answer all the questions after the session is ended, which will last about 30 minutes. And today's session will be recorded and available after the event. And I'd like to introduce today's speaker. Adam Kraft is a machine learning engineer on the Google Brain team, working on AutoML for a wide variety of AI tasks. Before Google, Adam spent 8 years in computer vision and machine learning, working with satellite imagery at Orbital Insight and helping customers shop with their phone cameras at Amazon. And okay, a little background before, just a background information on Clarify before we get started. Clarify is the leading independent provider of AI for unstructured image and video data. It's an end-to-end computer vision and NLP platform. It covers the entire AI lifecycle. Clarify has won numerous awards and is recognized by Forrester as a leader in computer vision platforms, in line with companies like Google and Microsoft. The company was founded in 2013 by our CEO, Matt Zeeler, PhD, after winning the top 5 places at ImageNet. Clarify continues to grow with over 80 employees at our headquarters in New York City, our offices in San Francisco, DC, and Tallinn, Estonia. And AutoML aims to help everyone achieve state-of-the-art AI for specific problems. Techniques such as neural architecture search, or NAS, have pushed the boundary of finding high-quality neural networks. When are techniques like NAS useful? What are the challenges of applying AutoML to new problems across the industry? This talk will explore these questions. Welcome, Adam.
Thank you, Jeff. Thanks for the introduction. Thanks to Clarify for having me. And I'm excited to give this virtual talk. So the work I'm presenting today is done by many people across Google, across the research teams, etc. And it's talking about where are we with AutoML. So a little background and history about some of the different generations of AI and how we got to where we are today and where we're going to go in the future. You can kind of think of these are loose classifications. They're not hard, set in stone. They definitely overlap. But in the beginning, when you think about like intelligent programs, intelligent things that you might call AI, a lot of these programs started out with very handcrafted things, predictions, sort of like if-else statements that would allow the programs or the agents to sort of act intelligently. But in reality, there really wasn't anything that was learned. There wasn't really this data collection and crunching numbers and trying to adapt given data scenario. It was mostly just, I can write a bunch of these rules and using my human knowledge to create a program that acts intelligently. And then going into generation 2, that's when you have, I guess, what we now call sort of these shallow learners, like classical machine learning predictors, where things like SVMs and other methods were doing some learning given some data, but a lot of times the tricks and the algorithms and the programs were built around how do the humans take the raw data and handcraft these features. So if you think of, data coming in from the world, like image, audio, video, things like that, humans would then handcraft these features, take that big data sources, and then boil them down into some feature vectors that could be then passed into these shallow learners. So things like, given this image, how can I characterize it in a way, given its characteristics about its colors or its shapes or edges, and then feed that into a prediction algorithm. So this is great because you are learning something given some data. However, there's still this handcrafted feature step where you have to figure out, given my intuition, maybe these are good things that will help the machine learning algorithm down the pipeline. And then more recently, we get into deep learning, which can really be thought of as sort of this end-to-end learning of, given the raw data, learn how to extract the features automatically, learn how to feed that into some prediction output. And then you have more or less an end-to-end pipeline, given data, extract the features, do the prediction. But on top of that, there is still this handcrafted piece where we're experiencing this today, where humans have to sit down and decide, oh, like if it's a neural network, which architecture am I going to use? Given the data, maybe there's some pre-processing I want to do. The learning algorithm itself, like which type of method do I use to actually learn the weights of my model, things like that. And so then looking forward into sort of the next generation of AutoML or learn to learn, the goal is that there's a lot less or almost nothing that's handcrafted. The goal is that you really have this system or this pipeline where you can just feed in data. It learns to obviously do the things in the previous generations, like feature extraction and the prediction step, but also it learns which components of the learning algorithm itself it should use to achieve the best results. So that's sort of a quick background. And then the question is, how do I go to the next slide? Okay. The question is, why is this important? The answer is that there's a lot of organizations that have some sort of machine learning problem or task that could be helpful to actually use, machine learning and AI. This could be, obviously places like companies, but also organizations like schools and clubs and, other groups of people getting together around the world that have some need to say, hey, how can I make smarter decisions given, what we're trying to achieve? So there's a lot of groups and organizations that have things that machine learning could be useful for, but there's really a small set of actual people or organizations that have the training, have the skills to apply these tasks and these problems. And on top of that, even so the question is kind of answering itself of, how can we meet the future demand of ML expertise for maybe groups that don't have the know-how, the skills right now, but also for the people that are applying machine learning and AI right now? How can we enhance those teams, those people? How can we make sure that everyone has the ability and know-how to achieve sort of the state-of-the-art results in terms of, maybe there's a few people that know some secrets in terms of how to tune these architectures or tune these learning algorithms. But how can we make sure that everyone has the best tools possible? And if you think about this, a lot of people that are attending today at this conference or watching this in the future might say, yeah, well, I'm lucky to be one of the people that knows about machine learning, that knows how to apply it, which is true. But even, all of us that have tried out problems and played around with some of the stuff, there are times where just some things kind of magically work and other times they magically don't. And it can be a pain to sit there and try to tune a lot of these different parameters. So how can we, even as practitioners that have some of this know-how, let the AI itself do some of that painful tuning process, and we can focus on smarter parts of the pipeline of thinking about the problem itself and the holistic view to this task that I'm trying to solve. Whether it's looking at things like medicine or satellite imagery, or data coming in from a manufacturing pipeline. How can I think about the holistic view as opposed to what activation function do I need to use at this part of my architecture? And in practice, recently, there have been a lot of AutoML driven pipelines that have achieved state-of-the-art results. So it's not just about, hey, I want to replicate the machine learning experts. So this graph shows some of the ImageNet architectures, the top accuracy on the y-axis, and essentially the model size on the x-axis. And that lower curve shows a lot of the sort of hand-tuned, human-designed architectures, which honestly did perform really well, did amazing things. And then more recently, some of these AutoML pipelines have shown that not only can they match the ML experts, but actually in some cases get better results, whether it's more efficient in terms of the model size or even a higher accuracy overall. And so, yeah, I mean, the goal is obviously to hopefully get as good as the experts, but maybe in some cases actually outperform them. Okay, so now that we know sort of why AutoML is useful, the question is now, where can we use AutoML? And the answer is more or less everywhere. If you think about a machine learning development pipeline that you have, in a very simplistic view, you could break it into these steps where you have your data pre-processing, you have your modeling, and then on top of that, you have some optimization algorithm where you're going to try to figure out how to essentially learn the best weights for your model to achieve the task at hand. And now I'm going to show a bunch of different examples of AutoML being used in different parts of these pipelines. So in terms of the data input and the pre-processing, you can think about things like augmentation and things like semi-supervision and self-supervision. So in this case, this is a paper from a few years ago called AutoAugment, where a lot of pipelines nowadays, people will create their own pre-processing and augmentation tasks to essentially generate lots of data to synthesize, having larger data sets. And so the question in this paper was kind of like, well, can we use AutoML to do that automatically? And so this was applied in this case on ImageNet and achieved state-of-the-art results by learning these policies of these augmentations by using AutoML. And we'll get into more of that in the future talk slides about how does that actually work? What does that actually mean? But the answer is yes. Instead of having to sit down and think like, oh, well, my data set, I'm going to try things like rotation or color enhancement, etc. Why not just sort of have an algorithm or a system that can kind of learn some of those on their own? This can be particularly useful if your data is not necessarily similar to ImageNet. So for instance, things like medical imagery or satellite imagery, maybe you don't want to do as much, warping or skewing, whereas maybe you can actually get away with doing more rotation. Like for ImageNet, you maybe don't want to like rotate images of cats upside down, but maybe that's okay in some, medical imagery cases. So these things kind of go into the sense of how can I let AutoML sort of take over some of these options for me? More recently in the augmentation space, this has been applied to other data types. So in this case, this is work being applied towards 3D data sets. So this is being applied on the Waymo open source data set. And I encourage you to check out the paper. And there's also a blog post because this is supposed to actually show an animation where there's different types of augmentations, where there's like random flipping and some, these are the LiDAR laser points being dropped out. And the thing that's interesting about this one versus the previous one is that the search space in terms of like how many possibilities there are for 2D, it's relatively manageable, whereas for 3D, there's just so many more choices and operations. You have an extra dimension and you have these different parameters. So the search space in terms of what is possible is very large. And therefore, like using AutoML to help you find the best policy is also beneficial, just because humans trying to manually search around and trying to find these things there's just more to search and it's harder to find good policies. Also on the data input side is the concept of semi-supervision or self-training. So this concept is I have data that I want to feed into my pipeline. And a lot of people will know that more data you have usually yields better results. And so that's even why augmentation is successful, because you're sort of synthesizing larger data sets. And so this question and this paper here, this self-training with the noisy student improves upon this by taking a model that is trained on ImageNet and then taking a much larger unlabeled data set and trying to self-label some of those examples in that large data set, and then retrain with all of the original ImageNet labels plus these what are called pseudo labels from this other data set, and iteratively doing this over and over and over. And this allows you to actually achieve better results than if you just trained on ImageNet alone. And this can also be extended into other domains, so not just image classification, but object detection, semantic segmentation. And this is a trend that we continue to see for more domains. This concept of it makes sense. We want to feed more data into these algorithms, but sometimes the cost of data labeling can be very high or prohibitive. So how can we use unlabeled data and feed them into our systems? And so in this case, it achieves state-of-the-art results for object detection, for semantic segmentation. And the interesting thing here is that sometimes you can actually look at these labels, these pseudo labels, and there's some interesting characteristics that come from it. So in this case, the middle column shows what was the ground truth from the human label. And then after training the initial network and then trying to use that to generate pseudo labels, you can actually see in some cases you might get more fine-grained or even better labels than the original human labels. So you can see that the bike is more outlined on some of the wheels, and the people, those shapes as well kind of give you more information, or there's more class information. So yeah, in general, when you think about the data input pipeline, there are ways to apply AutoML to either feed in more data, plus also use augmentation or learn augmentation that allows you to achieve better results by learning some operations that might give you better results during your training. Moving on to the modeling. So in terms of modeling, there's I highlighted two AutoML ways to add modeling to your pipeline. So one way is to think about, we have these usually we have these neural networks with these different blocks or different components that sometimes are hand-tuned by just trying things out and seeing what works. But you can also use AutoML to learn some of these individual components. So this is a fairly basic case, but as we all know, there's especially in convolutional neural networks, there's a lot of activation functions. So in this case, this image, the blue line, shows the ReLU activation function. And in this work, we actually used AutoML to learn a new activation function where it tried different combinations of different parameters and different functions. And it learned this function, which ended up giving us better results on new tasks. And this, what is called the swish activation, can now be used in other parts of machine learning pipelines, and people are getting good results in many cases. And it's actually interesting because it's very similar to ReLU, but it has this, lower dip right below 0, and then it kind of gradually goes up towards ReLU. So you can think about AutoML as learning individual components of a neural network that might then be useful to use for other pipelines down the road. And then moving on to a very big topic, which is neural architecture search. So this concept is essentially, instead of trying to either hand design a network or use a network that someone's previously built for me, can I use AutoML to learn the best architecture for my specific task? And there's a lot of reasons why this question and approach might be useful. For instance, maybe you think your data set is, characteristically different than things like ImageNet. So maybe the amount of layers, maybe the areas where it downsamples or upsamples or whatever might not be the same in your case. Also, another big constraint that a lot of people experience in industry is what if I want my problem or my architecture to be constrained either by the size of the model or the runtime? And so instead of taking an architecture that, exists and trying to hope that it fits within my runtime constraints, can I learn automatically to build the best architecture given a budget of something like runtime or flops, so that the model's learning to optimize my problem for some metric like accuracy plus some constraint with something like runtime. So this is a very big topic, which I'll go over more later in the slides. But this is really sort of getting towards the end to end, where AutoML is like building the entire or parts of, or even the entire uh, architecture for you. And then highlighting on the learning algorithm, AutoML has also been applied to, oftentimes we use off-the-shelf algorithms, things like, SGD, Atom, etc. And the question is, can we use AutoML to learn different parts of the optimization or the update rule, or different other parts of the learning algorithm in terms of like when we update different weights? And so this is one example showing that, you could, in this case, learn just some parameters of the update rule and get better results using AutoML. One other slide I wanted to show you, which is fairly recent and kind of goes even more holistically than what I just showed in terms of like taking AutoML and applying it to different parts of the pipeline. This is a work called AutoML 0. And in this work, the researchers basically took very low level functions in terms of, we're trying to build a program from scratch that learned to do everything. And this is kind of the futuristic end-to-end. How can we tell a machine like, hey, here's some operations that you can do, and here's some benchmark that I want to be optimized, and it's learning a lot, almost everything, like from scratch. So to give a quick overview of the method, the empty algorithm is that there's three sort of methods, which are setup, predict, and learn. And the program needs to fill in what each of those functions do, given a list of some very basic operations. And then eventually the algorithms are, is run predict, and it's evaluated on some test set. And it is using AutoML, in this case, an evolutionary algorithm, to try to write the best program that can perform the task. And the really interesting thing, so this graph, what it's showing is that it's showing on the y-axis the accuracy of the best overall program, and on the y-axis is the number of experiments that have been run. So it's essentially like over time, how is the whole evolutionary system performing? And there are different points labeled on this curve where the researchers actually went in and looked at what the program was doing, and it looked and found that, hey, this program actually learned to do some things that us humans essentially have been doing for our machine learning tasks. So looking in, things like loss clipping, defining random learning rates, ReLU, eventually getting into gradient normalization, and some very interesting things that are going on. And then there's also other calculations where the program does things that aren't as intuitive to see and require more digging into. But applications like this show what the future might entail in terms of like having even lower level abstracts where these machines and these systems can learn how to perform the task, with us really sort of being hands off. Okay, so that was an intro in terms of where AutoML can be applied. But now I want to give you sort of a deeper understanding of how AutoML works. And so in this setting, this is sort of one way to characterize the problem. However, oftentimes, things like even the AutoML 0 work that I just showed don't necessarily fit this paradigm per se. But essentially, when you think about AutoML, there's a task that you have. There's some data set, some task that you're trying to perform. And in a nutshell, one way to think about AutoML is to take that task, put it inside of this inner loop, and then run some outer loop, which is trying to learn how to improve the parameters of that inner loop to perform the best. So that outer loop, we can think of having a controller that's driving this system, where the controller says, hey, inner loop, try these parameter choices. And then the inner loop is going to run them, and it's going to give some feedback saying, oh, given these parameter choices, this is how well I did on the task. So looking at the controller, there's a lot of different choices just in this piece of the puzzle. So a very simple setting, which you could argue is not necessarily AutoML or not really learning much, is to do something like grid search or random, where given the parameter choices that you have, just exhaustively try all of them or randomly try them and just sort of see what works the best. You can also have this component be a machine learning model on its own. So something like using reinforcement learning, where it learns to output a set of parameters and you're giving it some feedback and it's learning to update to then try to choose the best parameters. Evolution is also a very popular controller choice because you can essentially look at creating all these populations of these different inner loop tasks and collecting the feedback and figuring out which things work the best and try to combine those for future generations and actually evolve them. So that's one pretty popular way to sort of drive the controller. And then there's also gradient-based methods where you're using probabilistic ways to try to model the parameter choice distribution and learn what parameter choice, draw from this distribution that you're learning to then feed to the inner loop.
And hey, Adam, I hate to interrupt the thought, but we are kind of running out of our time a little bit here, just as a heads up.
Okay, great. So going through, yeah. So on the parameter choices, this is really defining the search space. So this is something you might have to do before you set up. You might want to say, here are all the different things that I want to try. And that defines the search space for the controller to choose from. So this could be things like number of convolution filters, number of total layers, and the augmentation, which operations to try. And so this is what the controller is going to use to pick choices from. And then the feedback is simply sort of some metric that you care about, which could be something like accuracy, but then you can also do things like add penalties in terms of memory or runtime constraints. And so for memory, this is one paper example showing that you can take the constraints and in this case, it was trying to figure out how to find the best model that runs on a mobile phone. And so you could take the trainer, run the model on the mobile phone, collect the latency, and that's a part of your reward that goes back to the controller. Okay, so let me see how many more slides I have and time-wise. Yeah, so one thing to consider about cost, if you have this big outer loop, then doesn't that just explode the cost in terms of even to train your model? And the answer is that, yes, especially with some of the earlier methods, this can be a concern. And so now a lot of the research is focused on how can we make these costs lower? Either can we make that inner loop smaller and quicker to run? Or is there something that we can do, like in this slide, where you actually are jointly optimizing the inner loop and the outer loop in a more cost-effective way. All right, let me finish up with my few slides about what is sort of next for AutoML. So in terms of like what's next, AutoML has already made huge impacts in things like vision, video, text, tabular data, and more. And the question is, can this be pushed into new areas, new types of tasks, new types of data? In terms of cheaper, can we make it easier to compute in terms of the algorithm's output, or just to run these AutoML pieces? How can we do that? Labeled data can be cost prohibitive. So I mentioned ways to reduce the need for, or ways to use data more effectively or reduce the need for less labeled data. And then you can also think about if we can make some of these methods available for, especially groups that don't have machine learning experts, then that makes it cheaper for them to get access to machine learning and AI. Which is kind of what I'm saying here in this slide. But yes, the goal is to make AutoML available and to really everyone. And so there's the methods, but also making these available into more common machine learning libraries. So defining ways of these abstractions that we can just say, oh, I have this TensorFlow lib, and with very little effort, I can try AutoML. It doesn't need to be this cost prohibitive engineering cost. Great. So in conclusion, AutoML can match and in many cases exceed some of the ML experts. It can allow non-experts to help solve machine learning problems. And in the future, hopefully this will become easier, requiring less data and time for each new problem. So great, that's all I have. Hopefully we still have time for questions. And thanks, Jeff, for the timing constraint.
Sure, thanks so much. These are big topics, and we could certainly spend a year really getting into all of it, right? But we did have a couple questions come in here on the thread, and I wanted to address a couple of these. One of them is just, can it address computer vision problems? And certainly that's the case. One customer, Pranit here, is asking what hyperparameters are optimized by AutoML?
Yeah, great question, Praneet. So honestly, really the parameters that you want to search, anything is really the limit with AutoML. So if I go back up to one of my slides, which I kind of glossed over, you can really define that search space. In practice, to be honest, a lot of times searching over just a very specific thing may yield better results. Part of that might just be because, if you have a smaller search space, it's easier to find a good answer. But there is recent work where, for instance, it's annoying to have to pick things like learning rate and step size, or how to update, different things of the learning algorithm itself. So there are some promising methods where we've been able to create a search space which is jointly optimizing the hyperparameters of your system, things like learning rate, regularization, as well as the architecture search itself, all in an end-to-end manner. And I think in the future, as the research community explores more and as we try more of these things on real applications, we'll start to understand what is possible in terms of like, do you need to start with smaller search spaces, or is it okay to have these large search spaces?
Great. Okay. Do you see, since this is from Rahul, do you see any explainability issues with using AutoML?
Do I see any explainability issues with using AutoML? In some cases, there's some intuitive outcomes, like things like augmentation, where you're searching for some operations. It kind of makes sense to say, oh yeah, like those operations make sense for this data set, and then you tie a different data set and there's a different set of operations, and just by looking them, you say, yeah, like this data set, maybe you don't need rotation as much, or maybe you need more color contrast in that. But explainability is definitely a difficult topic in machine learning in general, and so that can be a similar challenge with AutoML. But a lot of the times the things that really delight and excite people that use AutoML and get good results is, hey, like, I had this model that I was, hand designed, and then I ran AutoML and it gave me higher accuracy and it runs faster. So you get like the best of both worlds. So explainability kind of comes into, being delighted by the results first, and then going in and looking what the architecture did, and you say, oh yeah, that's like an interesting choice that allows it to be faster, and it's not it sort of makes sense as to some of the choices that it made.
Okay. How about, does it use F1 or confusion matrix?
Does it use F1 or confusion matrix? Is this if this is related to sort of the feedback, it really depends on the task. If I'm understanding the question correctly, but for this, task that you're training, you need to figure out what's the metric that you care about. So that could be accuracy. It could be F1. It could be area under the ROC curve. It could be some metric that you care the most about, and you need to give this as feedback or as a reward to the controller. So it's really up to you in the design process.
Okay. And then one last question, and I think we'll have to wrap up our session here. And another great one from Praneem. Do you see a stage where results will be independent of data size?
Claudia.
Interesting. Sorry, is there someone? Hello, can you hear me, Jeff?
It's good. This last deck is a little bit
I can hear you.
Scramble.
Yeah. Next one will be prior planning.
Okay, so to answer the question about data set size, yeah, that's a tough one. I think data set size, there's the data set itself, but then you can do things like feed in unlabeled data or use augmentation to sort of augment your data set size. Honestly, I think, but this is my opinion, that I believe machine learning tends to do better with larger models and more data. So I think we'll see this trend continue. I think AutoML will help this area by allowing potentially to get better results with smaller data set sizes, or potentially to do better data augmentation or do better pseudo labeling or self-training using unlabeled data. And I hope that's a trend that at least in the near to short term will continue to improve results. Independent of data set size, that's going to be a tough one. We'll have to see in the future. Thanks for the question.
Cool. Well, Adam, thank you so very much for attending the conference today. Sorry about a little bit of a confusing audio issue there, but the recording will be available after the event for everyone to view later. And I am just going to hop off, and we're just going to do closing remarks. And thanks again. Thanks a million.
Thanks, everyone.
All right.